Okay, I'm going to be working section 12.5, triple integrals. I'm going to start out by doing number 4. You're supposed to do number 3 and 5, so I figured I'd do 4. So here it is. I'll point out that the order of integration here we have to pay attention to. So I'm going to start by doing the inner integral first. 0 to 1 here, 0 to 1 here. Now what I need to do is take the antiderivative of this with respect to x, and since these are all, no x's appear over here, this is all a constant, so the antiderivative of that is just going to be z times x over y plus 1, evaluated from x equals, let's see, x is our variable, 0 to that, so 0 to square root of 1 minus z squared, and then I'll do dz dy. All right, so if we plug in for x, this root thing, it goes there fine. Plug in 0, everything goes away. So we're going to have integral 0 to 1, integral 0 to 1 again, of this with x replaced. So z root 1 minus z squared over y plus 1 dz dy. So now I need to integrate this thing with respect to z. So y plus 1 is a constant, and I need to integrate that. That's going to be a little bit of work. So what I'll do is I'll work that out over here. If I'm trying to integrate z root 1 minus z squared with respect to z, and bringing out the constant, which is 1 over, or y plus 1 on the bottom, bring that out of the integral, it's 1 over y plus 1. And now for this, I'm just going to do a basic u sub. U is equal to 1 minus z squared. The derivative of that is negative 2z dz. And then I get negative 1/2 du equals z dz. So you can see I've got z dz there, and I've got 1 minus z squared there, that's u. So this integral turns into 1 over y plus 1. And then I replace the z dz with negative 1/2 du, so I'll pull the negative 1/2 out. I'll make this all negative. And then I have the square root of this, which is u, and then everything else was just du. The antiderivative of the square root of u is 2/3 u to the 3/2. So we get that this equals negative 1 over y plus 1 times 1/2 times 2/3. I'm out of room. Well, no, I can do this. U to the 3/2. I think that fits on there. Let's see if it's on. Yeah, that fit. Okay. The 2's cancel. And so I get negative 1 over y plus 1 times 3. I'll put 3 times y plus 1. And then u to the 3/2, but u was this, so 1 minus z squared to the 3/2. All right, this is the antiderivative of this with respect to z. So my next line will be, I'm going to write it right here. That this is equal to integral 0 to 1. I took the antiderivative of that and got negative 1 over 3 times y plus 1, and then 1 minus z squared to the 3/2, evaluated from z equals 0 to z equals 1. And then I'll have to integrate after that. So if z is 0, this is just 1. 1 to any power is 1, so all I get is this. Sorry. No, that's wrong. I forgot to put 1 here. If z is 1, that's 1. That 0 kills everything. If z is 0, then that's a 1, and then all I get is this. So I should have that this equals the integral from 0 to 1 of, remember when we plugged in 1, we got 0. Minus, when we plug in 0, we get negative 1 over 3 times y plus 1. And then with respect to y. Now that is equal to, the minus and minus become plus, so I get 1 over 3 times y plus 1 dy. And I can go a little further here. I can pull out a 1/3, integral 0 to 1, 1 over y plus 1 dy. And then from Cal 2, hopefully you recognize that's just going to be 1/3 natural log absolute value of y plus 1. And we're evaluating that from y equals 0 to y equals 1. Now if we plug in 1, we get 2 here, natural log 2. So we get 1/3 times natural log 2. Plug in 0, we get 1. Natural log of 1 is 0, so it's gone. So this should be the answer. Okay. Your next problem, 7. I think I will do 11, or I will do 8. So 8 is triple integral over e of e to the z over y dv, where e has these conditions. Y is greater than or equal to 0, less than or equal to 1. X is greater than or equal to y and less than or equal to 1. And z is greater than or equal to 0, less than or equal to xy. Make sure I got all that right. Okay. So we have that y is bounded between two constants. X is bounded between two functions of y. And z is bounded between two functions of x and y. So that means this is going to dictate the order of integration. I know that my integral, triple integral, must go dz first. Well, I'll do it this way. So dy last, dx, dz, and I'm integrating e to the z over y. My limits on y were 0 to 1. My limits on x were y to 1. My limits on z were 0 to xy. So that's what I'm trying to do. So let me first try and do the inner integral, which would be this one. Okay, what is the antiderivative of this with respect to z? Well, that's the same as e to the 1 over y times z. And 1 over y is a constant. So what's the antiderivative of e to the z? It's itself. But I have to account for that constant for chain rule. So one way you could do this to kind of give yourself an example. Let me just go 1/5 z. The antiderivative of this, okay, is first itself. But if you were to differentiate this, you would do the derivative of this is itself, then times derivative of what's up here, which would be a 1/5 that would pop out. You want that 1/5 to go away, so you have to scale it by 5. So if I'm trying to integrate this, I'm going to have itself, which I'll put z over y. But then that 1 over y is going to pop out when I take derivative, so I need a y out there like that. All right, so here's what we've got. We've got this is equal to integral 0 to 1, integral y to 1. Then the antiderivative of that, which I just said is y e to the z over y. And I'm evaluating this from z equals 0 to z equals xy. Okay. So now dx dy. I'm going to continue this up here. This equals, All right, let's plug in things here. We've got integral 0 to 1, integral y to 1, and then what happens when I plug in x times y for z? X times y there, the y's cancel, I just get an x up there. So it'll become y times e to the x minus, now plug in 0. If z is 0, this is going to give you e to the 0, which is 1, so all I get is minus y. Now I'm going to integrate that with respect to x and then with respect to y, and that's nice. Because the antiderivative of this is going to be a lot cleaner than it could have been. The antiderivative of this with respect to x, the y is a constant, so antiderivative of e to the x is itself. So I have y e to the x. And then the antiderivative of negative y with respect to x is negative yx, or negative xy. I'm evaluating this. Let's see, my x restrictions go from x is y to x is 1. And then I'll finally differentiate with respect to y when I'm done. So let's plug in 1 first. So this becomes integral 0 to 1. And then, all right, plug in 1 for x. We get y times e to the 1, which is just e, that's a constant, minus y times 1, which is y. And then we plug in x equals y, right? X equals y. So if x is y, this is y e to the y. And if I plug in y here, I get minus y squared. And then it's going to be all of that integral with respect to y. So let's see. This is going to be integral 0 to 1. I'm going to drop the parentheses here. Y times e minus y plus y e to the y plus y squared dy. All right, I'm making some progress here. I can take the antiderivative of this because e is a constant. So antiderivative of y is 1/2 y squared. Here, antiderivative of this is again minus 1/2 y squared. Antiderivative of that is going to be 1/3 y cubed. So I can take care of all those. This is the only one that I'm going to need a little bit of time to get. So I'm going to have to maybe do that over here. If I'm trying to integrate y e to the y dy, I'm going to use integration by parts. I'm going to let u be y and dv be e to the y dy. Now if I go up here, v, I get e to the y. And if I go down here, du is equal to dy. And so by the formula for integration by parts, it's going to be this times this. So y e to the y minus the new integral, which is going to be this times this, which is e to the y dy. And that turns into y e to the y minus the antiderivative of e to the y is e to the y. All right, so I should be good here. This should equal, okay, antiderivative of this, which was 1/2, I'm going to write it this way, e times y squared. Antiderivative of this, minus 1/2 y squared. Antiderivative of this, which we just got, plus y e to the y minus e to the y. And then antiderivative of this, which is plus 1/3 y cubed. I'm evaluating this from y equals 0 to y equals 1. So let's try y equals 1 in here. If y is 1, I get 1/2 e, or e over 2. Plug in 1 here, minus 1/2. Plug in 1 here, 1 times e to the 1, which is just e. And then minus e to the 1, which is minus e. And then over here we just get plus 1/3. It's all of that minus, now let's see what happens when we plug in 0. That's gone, that's gone, that's gone. This is gone. E to the 0 here is 1, so we're going to have minus 1, like that. I'm almost to an answer here. I think these e's cancel. And then I have plus 1 out there, so I've got, I'm going to write this 1/2 e now. Don't ask me why. Minus 1/2 plus 1/3 plus 1. So let's put all these together here. Right there, common denominator of 6. So negative 3/6 plus 2/6 plus 6/6. And you're going to get 5/6, I believe. Yes. I have a problem. Where's my problem? 8, 2, 3 minus. Everything was working out. Let me see here. E minus y plus, was that a minus in there? I miss a minus. Okay, hold on. This is supposed to be a minus right there. I think that was supposed to be a minus. I might have wrote it down wrong. Let me see if I can go back and recall real quick. Shit. Okay, we were at a point where we had integral 0 to 1, and then we had I really don't want to have to redo this video. Y e to the x minus xy, and we were plugging in x was y and x was 1. And then it was dy. So I'm just going to check to see if this was a negative. When I plug in 1 here for x, I got e to the 1. When I plug in 1 here, I got minus y. So that's this. So I had y e to the 1 minus y, and then I'm subtracting. I plug in y here, I get y e to the y. Y e to the y, and yeah, it should have been minus. And then when I plug in here, we get minus y squared. So I don't know why, but I put the plus here. That was right by distributing this through. But I don't know why I put plus there. So please correct minus. You probably caught that if you were really paying attention. This, and then that changes what part? Oh, the antiderivative. Oh, when we do the antiderivative of that, it's going to change that to a minus and a plus here, which is going to change this to, what is that going to change? This is the same. This is the same. This is minus. Minus, this is plus. And then that's still 1/3. No, hasn't changed yet. Plus 1. When you plug in 0, it's probably, oh yeah, that's what it is. When you plug in 0. When you plug in 0, everything goes away except this one, but it's a positive 1. So you're subtracting a positive 1. That makes this a minus. That makes that a minus. And that makes this. This is negative 7/6. All right, well, I guess I could redo the whole video, but I don't think I'm going to. Moral of the story is to be careful with your signs. You get the idea of what you're supposed to do. Let's see, 12, let me do 12. All right, for 12, you have triple integral over region E of xy dv, and E is the region that's bounded by y equals x squared, x equals y squared, z equals 0, z equals x plus y. So I have two what are called parabolic cylinders, that's these, and then I have two planes. So let me see if I can't get this, draw this out. It's going to be tough to draw. All right, so y equals x squared we know looks like a parabola, but the z is free here, so it's going to be normally in the xy plane it would just be this, but it's that with z coming out at us and going into the board. So on this drawing, it would be, my parabola would actually be laying on the ground going this way, like that. And then it goes up and down. So imagine this goes up, wraps around, comes down, keeps going down, wraps. So you've got this parabolic cylinder. And then this one in the it's y equals x squared. This one, okay, would be sideways, x equals y squared. So it's going to go like this. And then that picture over here would be going this way. So, and then it goes up and, you know, over and down. And so you can see there's some overlap in there. And then z equals 0 is the bottom, it's the floor. And then this is a plane. So let me try and draw that plane in here. Just pick some values. If x and y are 0, z is 0. Right, so that point belongs there. If, this can be a little harder to do. If, trying to pick some points. Let's say x is see, I don't have x-intercept, x, y, and z intercepts. That's it right there. So I can just pick some values. How about x is 1, okay, x is 1 and y is 0, then z would be 1. So it'd be up here. If y is 0 and x is, sorry, if x is 0 and y is 1, that's a point here, and then I go up 1. So there's 3 points there. It's a plane that's cutting through like this. So you can kind of maybe see this. You've got this little region in here, okay? Creates this little like tube, and this tube goes up forever and down forever. It's not really a tube because it's not a circle, but you get the idea of that's an intersection, and then the ground cuts the bottom of it off, and then the plane cuts it off again. So it's probably going to look something like this. I don't know, something like this. It might be slanted the other way. It's that sort of object. And what you can tell from this is the top of this, right, is capped off by this right here, this plane. So this was, if you go back and look at the notes, this is my u2 of xy. This is going to be equal to x plus y. The bottom of this thing is the ground, u1 of xy is 0. And so now we're just going to look at the domain, or actually the projection, the shadow down on the ground, which is this drawing right here, but I'm gonna make it a little bit bigger. We have this and we have this. And so I can look at this as a type 1 region. I know that they hit each other at 1. Okay, so I know from 0 to 1 is where I'm gonna integrate. I draw my little arrow in here. It's always the same curve on top and bottom. So I need to look at these as being G1 of x, and this top one is G2 of x. G1 of x is easy. That's the parabola x squared. This one came from the equation x equals y squared. I need to solve that for y again. So I get square root of x there. So I have, I believe, everything I need here. Let me see if I can write all my restrictions down. I have a triple integral where my x is between 0 and 1. My y is between two functions of x. The bottom one is x squared, the top one is root x. And my z is bounded between the 0, the xy plane, and x plus y. So my order of integration is now forced upon me. All right, I have to go integral 0 to 1. I've got to go integral x squared to root x. I've got to go integral 0 to x plus y. I've got to integrate the function as xy. And I've got to go dz, dy, dx. Okay, let's go at this thing now. Don't think I need any more of this. So this should be integral 0 to 1, integral x squared to root x. Integrating this with respect to z, which is just going to be x, y, z. From z equals 0 to z equals x plus y, dy dx, which is just equal to the integral from 0 to 1, and then the integral from x squared to root x. And now let's plug in x plus y for z, gives us something. Z equals 0 wiped out. So it's just going to be xy times x plus y, dy dx. So that's what I get when I replace that z with this. And then this is integral 0 to 1, integral x squared to root x of x squared y plus xy squared with respect to y then x. So let's now integrate this with respect to y. That should be pretty clean. So we should get integral 0 to 1, and then antiderivative of this with respect to y is 1/2 x squared y squared. And the antiderivative of this with respect to y is plus 1/3 xy cubed. I'm evaluating from y equals x squared to y equals root x. And then I'll differentiate, or I'll integrate with respect to x after I figure out all this. So this is equal to integral from 0 to 1 of, okay, what happens when I plug in root x for y? Oh, good, I square it, so it's just going to become x, and then times x squared, I get 1/2 x cubed plus, okay, when I cube x, great, that's going to become 1/3 x times x to the 1/2 cubed is x to the 3/2. And then I say minus, now I plug in y as x squared. I plug in x squared here, I get x squared squared is x to the 4th times x squared is x to the 6th, 1/2 x to the 6th. When I plug in x squared into here, x squared cubed, you multiply the exponents so you get x to the 6th, then times x, which is plus 1/3 x to the 7th, and all of that dx. clean this up a little bit. This is equal to integral from 0 to 1 of, okay, 1/2 x cubed. And then here, I can put these two together, that's x to the 5 halves. So plus 1/3 x to the 5 halves. And then here I subtract, so minus 1/2 x to the 6th. And then again, distribute through minus 1/3 x to the 7th. I have not taken an antiderivative, I'm just cleaning it up. And then now I take the antiderivative of that, and I use power rule. So here we get 1/8 x to the 4th plus, okay, we have to add 1 to this, which is going to be 7 halves, and then we multiply by 2/7, so 1/3 times 2/7 x to the 7 halves. Here we get minus 1/14 x to the 7th. And over here, 1/24 x to the 8th. And I'm evaluating x as 0 to 1. And if I plug in 1, things are going to happen. If I plug in 0, everything's gone. So it's just going to be these fractions. 1/8 plus 2/21 minus 1/14 minus 1/24. Which is going to become 3/28 if you go and add those up. All right, good, that one worked out. Okay, next one I want to do is number 18. Number 18, use a triple integral to find the volume of something enclosed. So solid is enclosed by y equals x squared plus z squared, and y equals 8 minus x squared minus z squared. So we've got to figure out what this thing looks like before we can actually come up with the volume of it and do it with a triple integral. But do remember that it's a triple integral over E of 1 dV. That will give us the volume of E. So that's what we're going to need to do. We just need to come up with some way of representing that object. So let's do this. You go back and you have to look at, the section on quadratic surfaces to figure out what these look like. Let me try and do this. Try and draw this. This is x, this is y, this is z. So y equals x squared plus z squared is going to be, let's say x and z are both 0, then y is 0. So we're at the origin. Okay, if x is 1 and z is 0, then y is 1. So if I go out 1 here, I'm over 1 here. Maybe there's a better way I can do this. How about I do this? What if y is 1? Okay, if y is 1, what does it draw? Well, x squared, it will draw x squared plus z squared equals 1, which is a circle with radius 1, but it's using your x and your z as the plane in which the circle is drawn, but is moved to the right one. So we draw this circle, radius 1, that's parallel to the xz plane. And then if I let, let's say y be 4, I'm using 4 because this will give us a nice radius. Then if I'm out here at 4, then it's going to draw a circle again, but this time the radius is 2. So if you put all these together, what you get is this right here. It goes out forever. So it kind of looks like this, sideways. And then if we do this one, okay, this right here, it's basically the same thing, except it opens the opposite direction. You can look at it like this. So this is going to draw you almost the same thing as that, except backwards. So it would draw it out that way. So it'd be like this. Okay. But the +8 on the y means that we're going to move this 8 to the right. So we're going to have another one of these going this way, like that. And so that is the solid we want. It's like these two bowls are put together. So that's the solid. Got to figure out what to do here. So what I'm going to see is that the best way to go about this is to look at the shadow of this cast onto the XZ plane. So imagine casting this down and across here. That shadow should be a circle on the XZ plane. That's the region I'm going to integrate over. But I need to figure out where they hit each other, okay? So I can figure out what that circle is. So I'm going to start this thing out by trying to set these equal to each other real quick. If I have x squared plus z squared, that's the first one, set that equal to the second one, 8 minus x squared minus z squared. Move my x squareds and z squareds to the same side, and then divide by 2. I know that I'm going to get this circle right here, which on the xz plane would be x squared plus z squared is 4, is a circle of radius 4. So that's my region of integration right there. That's the shadow on the ground. And then I have to figure out what the cap is, right? So normally we do top cap, bottom cap. On this one, it's right cap, left cap. So instead of top, right, instead of bottom, left. So this one right here, this surface, is the one with the minuses in them. So this is y equals 8 minus x squared minus z squared. And then the bottom cap, which is this one, is y equals x squared plus z squared. All right, I think from this I can do the problem. What I'm debating is the next section is polar coordinates, or sorry, cylindrical coordinates, and this is a really good problem for cylindrical coordinates. So should I do this one in cylindrical or should I stick to the harder way? I think I'm going to go cylindrical here. I really think I'm going to do that. So here's what we're going to do. Right now, as is, I'm trying to get restrictions on x and z and y, right? And this region right here is perfect for polar, right? But just be careful because we're using x and z here instead of x and y. So our polar conversions is that x is going to be r cosine theta, and z is going to be r sine theta instead of y. And x squared plus z squared will be r squared. So what is the region here? Well, theta is going to go between 0 and 2 pi. The radius is going to go between 0 and 2. Right? And now I need to get some control over the y values, the y, not the z, right? So the y values, the top cap I said was this one, and you'll recognize this is going to be y equals 8, and then when you convert that over, that's minus r squared. So 8 minus r squared. And then the bottom cap, or this cap on the left, is this, which is just r squared. And so what I have is this original integral is going to be switched over. We're going to go 0 to 2 pi for theta. R is 0 to 2. And then my y values, be careful, y values go from r squared to 8 minus r squared. What am I integrating? Well, I'm asking for the volume, so 1. But because I went to cylindrical, I need an r in here, so I'm just going to replace that 1 with r. And then it should be, let me go from the outside in, d theta, dr, but then this inner one is dy. And the reason, again, is because y is where our caps are Y is the variable that we're using to get our caps. So that's it. We set that up and we go. See how quick we can do this one. Okay, antiderivative of r with respect to y is ry. Evaluated from y equals r squared to y equals 8 minus r squared. Dr d theta. So this becomes integral 0 to 2 pi, and then integral 0 to 2. And now let's plug in for y, let's plug in this. So I'm going to basically get this times r, which is going to give me 8r minus r cubed. Then minus, plug in r squared here, we get r cubed. And then dr d theta. Minus r cubed plus r cubed. Or no, 2 minuses, sorry. So we've got, I was getting a little bit hopeful there. 8r minus 2r cubed, dr d theta. All right, this is still looking pretty clean. Integral 0 to 2 pi, antiderivative here is going to be 4r squared minus 1/2 r to the 4th. R being from 0 to 2. Oh yeah, this is working out nice. I'm going to let 2 go in there and get something, and when I put 0, nothing happens. I get 0, so I'll have integral 0 to 2 pi. Like I said, when I plug in 2 here, I get 4 times 4, 16, minus 2, 4, 16, half of that's 8. D theta, okay, cool. This is just 8 d theta. The antiderivative of 8 with respect to theta is 8 theta. I'm evaluating that from theta is 0 to theta is 2 pi. And I plug in, I should get 16 pi. All right, that hopefully is it. Yeah, good. This problem was hard because you had to project your shadow onto the XZ plane, and I really didn't do a bunch of those in class, or any of those, I don't think, in class, but you can hopefully see from this example how that works. Let me see, I think I have time to do one more. You're supposed to do number 41. Let's see if I can do 41. I'll actually do 41. Set up, but do not evaluate the integral expressions for the mass, the center of mass, the moments of inertia about the z-axis. So I'm supposed to look at exercise 19. Exercise 19 is the solid that's enclosed by, so our E is enclosed by y equals x squared, z equals 0, y plus z equals 1. So let me get a grip on the solid first, and then I'll come back to 41. So the solid looks like y equals x squared. We saw that a little while ago. That was this parabolic cylinder thing. Ooh. Something like that. It goes down forever. Z equals 0 is the ground. And then y plus z equals 1 is a plane. So let's try and figure out where that plane is. If y and z are both 0, no, I'm sorry, they can't both be 0. What about this? If z equals 1 minus y, that's a line, right? So the z value is 1 minus y. If y is 0, z is 1. And if y is 1, z is 0. And then your x is free. So basically you have a sheet that's coming through, this line goes through, and it's cutting through that parabolic cylinder. So I'm thinking you've got something that looks like this. The ground cuts it off. Right? Something like that. Okay, so that should be enough for me to tell what this solid looks like. On the ground, the shadow is going to be this parabola like that. And then wherever this plane comes and cuts through. So where does the plane actually cut through? That would be at z is 0, okay? Right? So forget this for a second. Where the plane cuts through the xy plane, z is 0, and if I set z to 0, I get y is 1. So I get 1 here, straight across. That's where that plane would come and cut through. Right here, that's a straight line. So this is my region on the ground, right? And so this is going to be pretty straightforward type 1 region. X can go from -1 to 1, and y, which is this, is going to go from x squared, which is the bottom piece, and then the top is always 1. And then the z is going to be stuck between this top piece, which is this plane, right, solved for z, which is 1 minus y, and the, sorry, that's the top, 1 minus y, and the bottom piece, which is 0, okay, z equals 0. So this is z equals 1 minus y, and then the bottom of this, of course, is z equals 0. All right, that's just the region, all right? So what I want now in this is to know the mass of this solid. And the density function they give me is that the density of this thing is the square root of x squared plus y squared. So mass, by its definition, is going to be the triple integral over E. Give me a second. Hey, you got a question? Come on in. Let me finish this real quick. Yeah. The mass will be the triple integral over E of the density function with respect to volume. So we've got our triple is, here are limits of integration. So we've got -1 to 1. Let me see, what is this? 19, yeah. -1 to 1, x squared to 1, 0 to 1 minus y of the density function, which is x squared plus y squared, and then d, let's see, z dy dx. That's your mass. It says just to set up the integral, it says, you know, don't evaluate it. Next thing they want is the center of mass. Okay, so center of mass, we have to find a triple here like this. So x bar is going to be the moment about the yz plane over the mass. So the moment about the yz plane is going to be, so I'll say this, 1 over mass times the triple integral over E of x, and then the density function, dv. So the only difference here is that from this is that x bar should be 1 over the mass, which I'm not going to write that integral out again, times the same limits of integration, and then I just tack an x in front of this, x root x squared plus y squared d z dy dx. So that's x bar. Y bar, only thing that changes is this is the moment about the xz plane, so this is going to turn into a y, so you'd have a y here, everything else would be the same. Z bar would be the moment about the y plane, which would change this here to a z, and then you do the same thing. So that's your x bar, y bar, z bar. And then the last thing they want is the moment of inertia about the z-axis, which by definition is triple integral over e of x squared plus y squared times the density function, like that, dv. So you're just going to have this integral. There's your density function. You just tack x squared plus y squared in front of that. And that should be everything that they want. Let me just double check that that was everything they wanted. So, yeah. Yep, so without evaluating, you don't have to evaluate those, just set them up. And that's it for 12.5.